Hello everyone. So today we will study about states of matter. Disclaimer slide which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. So these are the major topics which we will going to study. So first is Bragg's law and its applications. The fundamental relation among the wavelength of X-ray, interplanar distance in the crystal, and angle of reflection is known as Bragg's law. The expression is written as like this, where the lambda is wavelength of X-ray used, theta is the angle between incident X-ray and the plane of the crystal. D will be the distance between planes of the constituent particles in a crystal, and N will be an integer which represents the serial order of diffracted beams. Various applications of Bragg's laws are: structure of solids are determined by X-ray diffraction methods. Structure of complex substances such as proteins and nucleic acids are also determined by this method. Classification of matter. So anything which has mass and occupies space is called matter, and these three states of matter are solid, liquid, and gases. Solids have definite volume, definite shape, and they are rigid. Liquids have definite volume but not definite shape, and they are non-rigid. Gases have neither definite shape nor definite volume, and they are non-rigid. It is simplest state and show great uniformity in behavior. Besides the three states of matter, two more states of matter have been found to exist. These are plasma and Bose-Einstein condensate. It was predicted by Albert Einstein and Indian physicist Satyendranath Bose. If plasma are super hot and super excited atoms, the Bose-Einstein condensate are total opposite. That is, super cold and super unexcited atoms formed by supercooling to such an extent that the atoms lose their individual identity and condensate to form a single superatom. Following two factors determine the physical state of matter: thermal agitation and cohesive forces. Due to the kinetic energy of the particles, atoms or molecules of a matter are in a state of continuous vibration and agitation. This increases with increase in temperature due to increase in their kinetic energy. Cohesive forces may be attractive or repulsive. They are intermolecular forces, and attractive intermolecular forces are called van der Waals forces. In a solid, cohesive forces predominate the effect of thermal agitation. Consequently, the particles are held together in rigid, highly oriented, and close packed structure. In a liquid, cohesive forces are no longer strong enough. However, there are still sufficient so that particles cannot escape each other's environment. They have sufficient mobility. In a gas, the thermal agitation dominates the effect of cohesive forces. Thus, the gas molecule acquire the unrestricted and independent mobility of vapor state. The nature of intermolecular forces, molecular interactions, and effect of thermal energy on the motion of particles helps to determine the state of a substance. Attractive intermolecular forces are known as van der Waals forces. Different type of van der Waals forces are as follows: dispersion or London forces. The forces exist between non-polar molecules and they possessing temporary dipole moments. The interaction energy of these forces proportional to 1 upon r to the power 6, where r is the distance between two particles. Second, dipole-dipole forces. The forces that exist between dipole ends of polar molecule are strongest of all the van der Waals forces. Dipole-dipole interaction energy between stationary polar molecules is proportional to 1 by r to the power 3, and between the rotating polar molecule is proportional by 1 by r to the power 6. Dipole-induced dipole forces. The forces that exist between polar molecules having permanent dipole and molecules lacking permanent dipole. Permanent dipole of polar molecule induces dipole on the electrically neutral molecule by deforming its electron cloud. In dipole-induced dipole interactions, the interaction energy is proportional to 1 by r to the power 6. Ion dipole and ion induced dipole forces. They are similar to dipole-dipole and induced dipole interactions, but involves only ions instead of only polar and non-polar molecules. These forces are stronger than the dipole-dipole interaction because the charge of any ion is much greater than the charge of a dipole moment. Hydrogen bond, it is a special case of dipole-dipole interaction. Gaseous state. It is the most disordered state of matter. Matter neither have fixed volume nor fixed shape in the gaseous state. It takes the shape and volume of the container in which it is placed. Gases exhibit the following characteristic properties. Gases expand indefinitely. They are highly compressible. They intermix freely with one another or move from one place to other without any difficulty. This property is known as diffusion. Pure gases or their mixture are all homogeneous in composition. Gases possess very low density. The density of gas when compared to that of hydrogen is termed as relative density. Due to collision of molecules on the walls of container, gas exert pressure, which obviously increases due to increase in temperature. Gaseous molecules move very rapidly in all the directions in a random manner. Gas have highest kinetic energy. Measurable properties of gases. They are described in the terms of 4 parameters: pressure, volume, temperature, and mass or mole. They are termed as measurable properties. Mass expressed in gram or kilogram and equal to the difference in masses of empty vessel and vessel containing gases. Volume equal to volume of container and is expressed in terms of liter, milliliter, cubic centimeter, cubic meter, or cubic decimeter. These are some ways by which we can write the one unit in terms of another unit. Pressure, it is force per unit area. Greater force acting on a given area, greater will be the pressure. Origin of force exerted by a gas is the continuous collisions of the molecules against the wall of the container. The units of pressure are atmosphere, mmHg, torr, etc. And here also, these are some ways by which we can write our numeric value or numeric unit in some other unit. Fourth and last is temperature. It is the measure of hotness or a coldness of an object. It is measured in Celsius scale or absolute scale, that is Kelvin. Celsius scale was earlier known as centigrade scale. Gas laws. Various types of gas laws are Boyle's law. At constant temperature, pressure of a fixed amount of gas varies inversely with its volume, that is P inversely proportional to volume. Can be written as PV equals to constant or P1 V1 equals to P2 V2, that is constant. The two conventional ways of graphically representing Boyle's law are P versus V plot, that is here, and P versus 1 by V plot, that is this. Second law is Charles' law. At constant pressure, volume of a fixed mass of gas directly proportional to its absolute temperature. So V is directly proportional to T, or V by T is equals to constant, or we can write V1 by T1 equal to V2 by T2. Charles found that for all the gases at given pressure, graph of V versus T is a straight line. You can see in this diagram V versus T graph at different constant pressure showing straight lines. Charles obtained experimentally that for 1 degree Celsius change in the temperature of gas, volume get changed by the fraction of 1 upon 273. Hence, V naught be the volume of the gas at 0 degree Celsius and it is recorded to be V at 3 degrees Celsius, then this will be the value which is coming out for V. V naught upon 273.15 T. If temperature lowered, volume decreases at constant pressure and becomes 0 at minus 273.15 degrees Celsius. This is the lowest temperature possible. It is known as absolute zero of temperature. Scale of temperature based on this choice of 0 is called absolute scale of temperature or thermodynamic scale of temperature. This is the expression by which, by putting the value in either Kelvin or degree Celsius, we can convert the temperature from one unit to the another. That is Kelvin to Celsius or Celsius to Kelvin. Third is K-Lusek's law. At constant volume, pressure of a fixed amount of gas varies directly with the temperature. That is, P is directly proportional to T. Or P by T equals to constant, or we can write P1 upon T1 equals to P2 upon T2. Fourth, Avogadro's law. It states equal volumes of gases at same pressure and temperature contain equal number of molecules. That is, V is directly proportional to N, or we can write V1 upon N1 equals to V2 upon N2. The Boyle's law, Charles' law, and Avogadro's law can be combined together in a single equation known as ideal gas equation, which is V is directly proportional to Nt by V. By rearranging the terms, we can write PV equals to W by M RT. W by M is the number of moles. So we can write PM will be equal to DRT, where W is mass of gas, M is molecular weight of gas, D is density, P is pressure, T is temperature, V is volume, and R is universal gas constant, having values, all these values in different measuring units. Dalton's law of partial pressure. Total pressure exerted by a mixture of non-reacting gases will be equal to sum of partial pressure of the individual gases. P total will be equal to the sum of partial pressures of individual gases. Partial pressure of gas P will be equal to mole fraction multiplied by P total, that is total pressure exerted by the mixture. If we want to find the percentage of a gas in a mixture, we can use this formula and this formula in terms of mole fraction of the gas. When a gas is collected over the water, the pressure of gas, which is observed or moist pressure, will be equal to pressure of dry gas plus aqueous tension or water vapor pressure. By this, we can write the relative humidity formula, partial pressure of water in air divided by the vapor pressure of the water. Graham's law of diffusion. According to the law, if a gas is allowed to escape from its container through a small hole into vacuum, the process is called effusion. On the other hand, diffusion is the passage of gas through porous partition. So rate of diffusion or effusion is inversely proportional to under root molecular weight. And we know molecular weight can be written as 2 multiplied by vapor density, that is M multiplied by D. So rate of diffusion or effusion will be inversely proportional to under root density. Therefore, rate of diffusion or effusion can also be written as volume diffused or effused divided by time taken. Hence, we can get this terms. And if P is not constant, then R will be directly proportional to P. That is, rate of diffusion or effusion will be directly proportional to P. And we can write this expression. Kinetic theory of gases. It is based on the following postulates. A gas consists of extremely small discrete molecules. These molecules so small and so far apart that actual volume of molecule is negligible as compared to the total volume of the gas. Gas molecules are in constant random motion with high velocities that moves in a straight line and change their direction on collision with other molecules and the walls of the container. Intermolecular forces of attraction are negligible and the effect of gravity on them also negligible. Collisions are perfectly elastic, therefore no loss of kinetic energy. However, there may be redistribution of energy during such a collision. The pressure of a gas caused by the bombardment of moving molecules against the walls of container. In a gas, different molecules have different kinetic energies, but average kinetic energy of molecule proportional to absolute temperature of the gas. On the basis of these assumptions, the following mathematical expression for the kinetic gas equation is derived. That is, PV equals to 1 by 3 m nu square, or PV equals to 1 by 3 mu square, because capital M or molarity can be written as m cross n, that is, for 1 mole m will be 1 and u is RMS velocity. So different kind of velocities of molecule are, first one, root mean square velocity. You can write the formula of root mean square velocity as under root 3 kT by m. For the same gas at two different temperature, the ratio of RMS velocity will be this, and for two different gases, the ratio of RMS velocity will be written as this. Average velocity, you can write the formula like this, and most probable velocity, that is under root 2p by d. If we want to find the relation between these different molecular velocities, we can find it in terms of ratio and under root and decimals. We can also say that UAV, that is average velocity, will be equal to URMS multiplied by root mean square velocity multiplied by 0.9213. Kinetic energy of molecules can be written as 3 by 2 kT, where K is a Boltzmann constant, and which will be equal to R by Na. Na is Avogadro's number, and R by Na have this value. So the Ke will be 3 by 2, this value multiplied by T. That is 3 by 2 RT. At absolute zero, the kinetic energy of the gas molecules become 0. Real gases. Real gases are gases that do not perfectly follow the ideal gas laws due to interaction between the particles and the volume occupied by the gas particles themselves. At very low temperature and high pressure, real gas show deviation from ideal gas behavior. The cause of deviations: at low temperature and high pressure, volume of real gas is larger than the predicted for an ideal gas, as the molecules of gas have their own volume. Intermolecular forces are not negligible. The deviations from ideal gas behavior expressed in the terms of compressibility factor, that is Z. So Z will be equal to PV upon nRT, and for ideal gas it will be equal to 1. So Z can be less than 1, greater than 1. Less than 1 can be attributed to predominance of attractive forces, and greater than 1 can be attributed to dominance of strong repulsive forces among the molecules. There is a Boyle's temperature, which is a temperature for the gas at which it obeys ideal gas nature. At this below this temperature, value of Z first decreases, reaches minimum, and then increases as the pressure increases continuously. To rectify the errors caused by ignoring the intermolecular forces of attraction and volume occupied by molecule, Johannes van der Waals proposed the following equation. So this is the equation where N is number of moles, A is constant, and B is also constant. Units of A are given here and B are also given here. Van der Waals equation get reduced at different conditions of pressure and temperatures. These are shown below. So firstly, pressure. When we lower the pressure, V will become large. Thus, V minus V will be equivalent to V because B is neglected in comparison to V. Therefore, equation will become 1 minus A upon VRT. And at extremely low pressures, A by V is very small as V is very large. Thus, it can be neglected and the equation will become PV equals to RT. When pressure is high, V is quite small. Thus, V minus B cannot be neglected and the term A by V square is quite large. But in comparison to high P, A by V square can be neglected. So, the equation will become Z equals to 1 plus PV by RT. When in the case of temperature, when temperature is high, V is very large, then the term A by V square and B can be neglected. Then our equation will come PV equals to RT. And when temperature is low, P and V are small, the both pressure and volume corrections are appreciable. The value of van der Waals constant A and B do not remain constant over the entire range of temperature and pressure. Hence, van der Waals equation is valid only over specific range of temperature and pressure. Liquefaction of gases and critical constants. The phenomena of converting a gas into liquid is known as liquefaction at particular temperature, pressure, and volume. When gas changes to liquid, these conditions are known as critical condition, TC, VC, PC, etc. Critical temperature, written as TC, is the maximum temperature at which gas can be liquefied. Critical pressure, written as PC, is minimum pressure required to liquefy a gas. And critical volume, VC, a volume of 1 mole of gas which occupied at critical temperature. So these are the formulas of critical temperature, pressure, and volume in terms of A and B. The relationship between the critical pressure, volume, and temperature is this. So Z, compressibility factor, is less than 1 at critical point. and there is no distinction between gaseous state and liquid state at critical point, as densities of a substance in gaseous and liquid are same. Liquid state. State of matter in which molecules are held close to each other and execute random motion. Liquids have definite volume. They can move past one another freely. They can flow, can be poured, and can assume the shape of container in which these are stored. Physical properties of liquid. Vapor pressure. Inside a closed vessel, liquid and its vapors are in dynamic equilibrium. Pressure exerted by the vapors on the walls of the container increases. After some time, it becomes constant and equilibrium is established between liquid phase and vapor phase. Vapor pressure at this stage is known as equilibrium vapor pressure. Since vapor pressure kinetic phenomena, it is independent of amount of liquid. It only depends on temperature. So when liquid is heated in an open vessel, the liquid vaporizes from the surface. The temperature at which vapor pressure of liquid become equal to the external pressure, vaporization occur throughout the bulk of the liquid, and phenomena is known as boiling, and the temperature is known as boiling point. Viscosity. Ease with which fluid can flow is determined by viscosity. It arises due to the internal friction between layers of the fluids. Viscosity of liquid decreases with increase in the temperature, because rise in temperature increases the kinetic energy of molecules. This results in decrease in interlayer friction. Surface tension. Force acting along the surface of a liquid at right angle to any line per unit length is surface tension. Unit is Newton meter inverse. Surface tension decrease with the rise in temperature, and they are different for different liquids. Due to surface tension, small drops of liquids are spherical in shape, as liquid tends to have a minimum surface area. And due to surface tension, liquid rise or fall in a capillary tube. Solid state. Defined as the form of matter which has rigidity, due to which it possesses a definite volume and a definite shape. Characteristic are due to the existence of very strong force of attraction among the particles of the solid. On the basis of arrangement of their atoms or ions, solids are broadly classified into two groups: crystalline, amorphous. Crystalline have systematic and regular arrangement of particles and sharp melting point. Crystalline solids are anisotropic, that is, physical property have different values in different directions. On the basis of types of bonds present, further divided into four groups: molecular crystals, atomic crystals, metallic crystals, ionic crystals. Amorphous solids are unsystematic and irregular arrangement of particles. They are isotropic. Physical properties have same values in different directions. Unit cell and lattices. An array of lattice points showing arrangement of constant particle in different position in three-dimensional space, known as space lattice or crystal lattice. Unit cell is smallest group of lattice points. A unit cell is characterized by its dimension and angles. 7 crystal system and their unit cell parameters is given here in this table: cubic, rhombohedral, orthorhombic, triclinic, monoclinic, tetragonal, and hexagonal, and their unit cell parameters are here. Solid state, various type of unit cells are as follows: simple unit cell, in which particles present only at corners and the number of atoms per unit cell is 1. Face centered, particle present at corners as well as center of each face. Number of atoms per unit is 4. Body centered, particles present at corners as well as one particle is present at center within the body. Number of atom per unit cell, 2. The number of atoms in a crystal which surrounds particular atoms as its nearest atoms in its neighbor is called coordination number. Each coordination number corresponds to a fixed radius ratio, that is ratio of radius of cation to that of an ion. This is a table giving here showing some range of radius ratio, depicting some coordination number related to that, and describing the structure related to that range of radius ratio. Packing in solids. The packing of sphere of equal size in solid takes place as follows: one-dimensional packing. When the spheres are placed in horizontal row, touching each other, an edge of the crystal is formed like this. Two-dimensional packing, it is done in two different types. Square closed packing. Particles when placed in adjacent rows shows a horizontal as well as vertical element and form squares. This is the diagram. And hexagonal closed packing. The particles in every next row are placed in the depression between the particles of the first row. Particles in third row will be vertically aligned with those of first row. Coordination number showed by HCP is 6. And this is the hexagonal closed packing diagram. Three-dimensional packing can be obtained by stacking two-dimensional layers one above the other. It is of two types: hexagonal closed packing and cubic closed packing. Hexagonal closed packing, in the hexagonal closed packing, the arrangement is AB pattern or hexagonal closed packing pattern. Cubic closed packing, the arrangement is ABC pattern. It is similar to face centered cubic packing, that is FCC. Voids. In closely packed structure, empty space is called interstitial site or voids. Void can be simple triangular space in case of two-dimensional packing and called trigonal void. This is a diagram of trigonal void. And in three-dimensional closed packing patterns, the voids can be of two types: tetrahedral. This is the diagram showing the tetrahedral void. And octahedral. This is the octahedral void diagram. The size of above voids can be seen in the increasing order as highest in octahedral, then tetrahedral, then trigonal. If n sphere is packing, then number of octahedral voids will be n and number of tetrahedral voids will be 2n. Relation between edge length and radius of sphere. Simple cubic, R will be A by 2. Percentage packing, percentage of packing fraction will be 52%. Face centered cubic, R will be A by 2 root 2. Percentage of packing fraction 74%. Body centered cubic, R is under root 3 by 4 multiplied by A. Percentage of packing fraction 68%. Density of unit cell, D, will be equal to M cross Z upon Avogadro number multiplied by A cube. D density, M molecular weight, Z number of protons per unit cell, N Avogadro number, and A is the edge length of the unit cell. Structures of some ionic solids. Rock salt, it has FCC arrangement and coordination number of 6 in the case of both ions. CSCl type, BCC arrangement, CS positive at body center and Cl negative ions at corners of a cube, or vice versa. Coordination number is 8 for both the ions. Zinc blend, it has CCP or FCC arrangement. Coordination number is 4 for both the ions and structure is identical to diamond. Fluorite, it has CCP arrangement. F negative ions occupy tetrahedral voids. Coordination number is 8 for cation and 4 for anion. Antifluorite has CCP arrangement. Cation occupy half of tetrahedral voids. Coordination number is 4 for cation and 8 for anion. On applying pressure, NaCl structure, which is 6:6 coordination, changes to CSCl, that is 8:8 coordination. And reverse of this occurs at high temperature. Imperfections in solids or defects. Any departure from perfectly ordered arrangement of atoms in a crystal is imperfection or defect. Defects are of two types: line defects and point defects. Point defects classified into three types: stoichiometric defect, and stoichiometric defects are also classified into two types: vacancy and interstitial defect. Schottky and Frenkel defect are vacancy and interstitial defects. So here is the table giving Schottky defect and Frenkel defect explanation, properties, and some examples. Non-stoichiometric defects contain constituent elements in non-stoichiometric ratio due to the defect in their crystal structure. These defects results in either excess of metal atom or deficiency of metal atom. Metal excess defect due to anionic vacancies. Negative ion may be missing from its lattice side, leaving a hole which is occupied by an electron, thereby maintaining the electrical balance. Electrons thus trapped in the anion vacancies are called F centers because they are responsible for imparting color to the crystals. Impurity defects. Common method of introducing defects in ionic solids, done by adding impurity ions having different charge than host ion. These foreign atoms present at lattice side in substitutional solids and at vacant interstitial sites in interstitial solids. Electrical properties of solids. Solids are classified into three groups on the basis of conductivity: conductor, semiconductor, and insulator. In conductor, conduction band is almost overlapping. You can see here with the valence band. There is no energy gap present between these two bands, or valence band is not completely filled. Electron can flow easily under the influence of electric field in both the cases. In semiconductors, you can see here the gap between the valence bond and the conduction band is small. Therefore, some of electron may jump from valence band to the conduction band and some conductivity is observed. Electrical conductivity of semiconductor increase with the rise in temperature since more electron can jump to the conduction band. Substances like silicon and germanium show this type of behavior and are called intrinsic semiconductor, undoped. You can see the silicon structure here. Conductivity of intrinsic semiconductor is too low, so their conductivity is increased by adding an appropriate amount of suitable impurity, and the process is called doping. Introduction of impurities in forms of electrons of 13 and 15 group of periodic table in perfect crystal. Such conductors is called extrinsic conductors. Depending upon nature of elements used for doping, extrinsic semiconductor can be of two types: N-type and P-type. N-type semiconductor, group 15 elements have one electron excess to silicon or germanium after forming 4 covalent bonds with group 14 members. This excess free electron is responsible for electrical conductivity in them. Group 14 elements, when doped with group 15 elements, are called N-type semiconductors. Here you can see the diagram of N-type semiconductor. P-type semiconductor, group 13 element have one electron short to group 14 elements, giving rise to electron deficient band or a hole. Here such holes are responsible for position hole. You can see the diagram of P-type semiconductor. Thus, group 14 elements, when doped with group 13 elements, are called P-type semiconductors. In case of insulator, energy gap between valence band and conduction band is so large that it cannot even covered up by supplying energy in the form of heat. You can see here. Magnetic properties of solids. Origin of magnetic properties lies in the electrons. Each electron in atom behave like a tiny magnet. Magnetic movement originates from two types of motion: orbital motion around nucleus, spin around its own axis. Electron, being charged particle undergoing these motions, can be considered as a small loop of current, possesses magnetic movement. Electron has a permanent spin and an orbital magnetic moment associated with it, whose magnitude is very small and measured in the unit called Bohr magneton. It is equal to this value. Solid can be divided into different classes depending on the response to magnetic field. Diamagnetic substances, weakly repelled by magnetic field and do not have any unpaired electrons. Paramagnetic substances, attracted by the magnetic field and have unpaired electrons. Ferromagnetic substances, attracted by the magnetic field and show permanent magnetism even in the absence of magnetic field. Antiferromagnetic have net magnetic moment 0 due to the compensatory alignment of magnetic moments. And ferrimagnetic substances have net dipole moment due to unequal parallel and antiparallel alignment of magnetic moments. The examples are also given. Dielectric properties of solids. These are seen in insulators. Insulators show generation of dipoles in them when they placed in an electric field. The dipoles are given below. May align themselves in an order manner so that there is a net dipole moment in the crystal. May align themselves in such a manner that dipole moment may cancel each other. It also possible that there are no dipoles in the crystal but only ions are present. Some other important dielectric properties of solids are piezoelectricity, produced on applying mechanical stress; pyroelectricity, produced on heating some polar crystals; ferroelectricity, piezoelectric crystals with permanent dipoles; antiferroelectricity, the dipoles in alternate polyhedra point up and down in such a way that crystal does not possess any net dipole moment. Okay, so we are at a summary slide. These are the major points which we have studied. Bragg's law, and in a mixture of gas, total pressure is sum of partial pressure of each individual gases. We studied the rate of diffusion of a gas directly proportional to square root of its molar mass. We can express it in this way. And packing in solids refers to the arrangement of particles within a solid, influencing its density and properties. And the presence of voids affects properties such as density and compressibility in a crystal. Okay, thank you.